Just the last couple of pages in Chapter 3 are some more reviewing of chemical equations. Let's get our names right here. A chemical equation represents a chemical reaction with chemical formulas. So let's make sure we're all good on that. The chemical equation is what we write down on paper. Okay? It's like this plus this makes that plus that, right? It has the arrow between the reactants and the products, right? The reactants are the substances that will react. So they're the things that you're sort of combining together. They're on the left. And the products are the substances that result, that are over on the right. Okay? The chemical formulas are the elements, compounds, okay, that are actually in these, the H2O, the NaCl. Okay? And those are the formulas. And then a chemical reaction is what actually happens, okay, in the lab. So you can't write down a chemical reaction. Okay? You perform a chemical reaction in lab, okay, with your test tubes and stuff like that. Those are chemical reactions. Chemical equations are what are the written form of that, essentially. Okay? So we will very typically use phase labels behind each of the formulas to say what phase everything is, right? Solid, liquid, gas. What does AQ stand for, though? Aqueous, which means dissolved in what? Water. So be careful, because something that is aqueous can look an awful lot like something that is liquid. Okay? This liquid is only for pure liquids, where the substance itself is in the liquid form, in its liquid form, right? Where it could freeze or it could boil, okay, go into solid or gas straight from there. Aqueous means anything that's been dissolved in salt water. So really handy way to remember those and to double check yourself is if you know the difference between NaCl aqueous and NaCl liquid. What does NaCl aqueous, what is that also known as? What would you casually call that when you're staring at the ocean or something? NaCl aqueous is salt water. What would have to happen to get NaCl liquid? You would have to take pure NaCl, right? That's a solid. Let's write pure ionic compound here. All the pure ionic compounds are solids. So when you got a metal and a non-metal just in its pure form, they're solids. So our stockroom is full of, hundreds, I guess, of ionic compounds that are pure. They're just solids. Okay? Most of them are white, some are colored, but the pure ones are solids. Okay? If it is able to dissolve in water, we can give it that AQ phase label after we've dissolved it. Okay? But the liquid is still pure, but now it is molten. So we have to heat it up above its melting point, at which point it becomes a liquid. For ionic compounds, that's pretty difficult. They have fairly high melting points. Sodium chloride has one of the lowest melting points of all ionic compounds, but that's still like 800 C, if I'm remembering right. So you need to do it in a ceramic crucible with a torch or something like that. Okay? So even though salt water, even though you can pour it, right, and you can splash it, okay, it's not the liquid phase label because it's not a pure liquid. It's mostly water with some NaCl dissolved in it. Okay? So make sure that everybody is good on that. Let's practice writing a balanced, well, we don't even need to balance this one. We'll balance on the next page. Let's just write the chemical equation with phase labels for when solid calcium reacts with chlorine gas to produce solid calcium chloride. Why don't you give that a try? I want to see if there's a couple little things to remember here. I want to see if we remember them or not. I have a feeling you'll do okay with solid calcium. Oh, well, that's unusual. Got another piece of paper you can write that on. Okay. All right, just as I suspected. So for solid calcium, right? Calcium, solid. Okay, reacts with, so that's a plus. Okay. I saw an awful lot of that, but that's not quite right. What is missing there on that chlorine? 2Cl? Not quite. You might think it's like that, but not quite. Yeah. So why do we have to do that? It just says chlorine gas up there in the problem. Why is it Cl2? Yeah, the answer is sort of on the periodic table here. So how many elements are diatomic elements? We talked about that. Remember this? Okay. What that means is that when we have any of those substances as an element, that's either a reactant or a product in a chemical reaction, okay, if we react something with chlorine or if we produce chlorine, okay, in a reaction, it's not just Cl. Cl atoms alone are unstable. All of these, what they do to become stable elements is they pair themselves up. So that's where the Cl2 comes from. It is if we have a diatomic element. Right? Now, the other thing I saw some people writing Ca2+ over here. Okay? When we have a pure element, that does not have a charge. None of the elements have charges to them. Elements are totally neutral. Okay? But when it's involved in a compound, okay, if we've made a compound out of a metal and a nonmetal, that's when we need to use the charges. Okay? So it's just sort of a coincidence that calcium is 2+ and that's diatomic here, but this Cl2 has nothing to do with calcium's charge. Okay? Chlorine reacting with anything would be Cl2. Okay? And calcium reacting with anything would be just Ca. Okay? If you ever happen to see a little, I suppose it looks like a degree sign, but it's a superscript 0. That also means no charge, neutral. Okay? It's actually its oxidation number, which we'll talk about later on, but sometimes it's written like that. Okay? Especially for pure metals. Okay? Just as a reminder that there's no charge to them, they're neutral. Okay? So then, calcium chloride, pretty much everybody wrote CaCl2 here, solid. Is this number 2 here because chlorine is diatomic? No. Okay? These number 2s mean a totally different thing. Okay? Here's a diatomic chlorine. Why do we have that number 2 there? Okay? This is to balance to neutralize calcium's charge. Okay? This is what's made up of the charges. Ca2+, Cl-. Okay? Now, I know that's reviewing type stuff, but those are the kind of mistakes that'll really mess you up. Okay? Pure elements are neutral. Compounds, if it's a metal and a nonmetal, we need to use the charges to make the formula of that compound correctly, okay? And so on. But I think I just picked this one because it doesn't need to be balanced. It's all ready to go. Okay? So let's practice a little bit of balancing. I think most of you have some experience balancing and can probably do fine with simple balancing. What's important to remember is that to balance a chemical equation, the only thing we can do is add coefficients in front of the formulas. So what we always have to do first is establish what the formulas themselves are. Okay? the reactants and the products. And that's always going to be our first step. What are the reactants? What are the formulas of the products? And then that gets locked in, and all we can do to get the left and the right equaling each other is putting the coefficients in front. So that's a very common mistake to start getting messed up, to start thinking about what these should be based on how many you have over here, and that's not the way to do it. Figure out what the actual formulas are, and then worry about balancing only with the coefficient in front. So only add those coefficients, never change subscripts. Okay? A compound is a compound, and we can't make a compound different. Okay? Unless you made a mistake or something, you need to leave that compound what it is. Save elements for last. So like this O2 right here, we can put whatever coefficient we want right there without messing any of the other elements up. So it's best to save that for the end. If we got fractions, those need to be multiplied through, so we got whole numbers. Polyatomic ions can be grouped together. If you've got sulfate on the left and sulfate on the right, count that as a sulfate group instead of counting all the 4 oxygens within them. That'll simplify any balancing issues right away. So most balancing, a lot of the time, you should be able to get to the point where you can do something like this in your head, but until then, you have to write out the elements, separate it into the 2 halves. Okay, start with, I'm just counting up how many atoms there are in each side. Don't forget, if you got an element in multiple compounds, to add all those up, right? I'm starting with 3 O's over on this side, for instance. Okay. So what usually works best is to just start going one element at a time. If an element only shows up once on each side, then you should be able to balance it with just one coefficient, usually. So how would I get carbon balanced, just starting out like this? Let's do 4 CO2 and then update our totals. That gave us, what would my new O total be here? Close. Yeah, don't forget don't forget the O over here, right? Because there's 8 O's over here, but there's still one more. What does no coefficient mean? Does that mean 0? No coefficient means 1. Okay? We're multiplying those coefficients, so don't forget that. So then what should I put for H to get H balanced? Let's do a 5, because then we got 10, and then now my O total is what? 8 and 5 is 13. Okay. So what would I have to do now? Because all's left is O. What should I do to get O balanced? Any ideas? If we just left it as it is, just like this, what would have to go in front of O2 to make O balanced? How would I get 13 O's? Yeah, it would have to essentially be 6.5. You could do 13 halves like that, but we need to multiply fractions through so that everything is simplified. So how would I get rid of that fraction then? Yeah. If we double everything else, that becomes 2, that becomes 13, that becomes 8, that becomes 10. Then we should be good, and you should be able to double check that we got 8, that we got 20, that we got 13 times 2 now is 26. Now I've got 8, now I've got 20. We got 16 and 10, 26. So that's the sort of thing that you're checking for ultimately to get things balanced. The coefficients go in front of compounds, okay? And those coefficients get multiplied through the entire compound. But what you're checking for to make sure it's balanced are atoms. Okay? Why don't you see if you can give that one a try? It's shorter, but curious to see what you come up with. Okay, so you got O2 on the left and O3 on the right. So what you could try is making the least common multiple of O's. Sometimes that works if it's not immediately straightforward what has to happen. What number? Oh, yeah, go ahead, Matt.
So with the 8 and the 10, is it, so the 8, so you have 16 oxygens plus 10, isn't that 26 oxygens?
Yep.
I see it.
Yep.
I was looking for each.
Yep.
All right.
Go. What coefficient would you like to put in front of O2 here? Anybody get it?
3.
If we put a 3 in front of there, that gives us 6 oxygens, right? So that means over here we need to put a 2 to get 6 oxygens, right? 6O is the, I think that's the least common multiple. But that's one way of doing it, especially if you got 2s and 3s, or if you got 3s and 4s, and things like that that aren't divisible into each other. Okay, you can make a least common multiple out of it. And then what else do we have to do? 4, yeah, there we go. So 4 irons, 6 O's, 4 irons, 6 O's. Okay. Why don't you give this one a try? Here is a description of a reaction. I've given you the names of the reactants and products, but it's going to be very important that you use the charges to write all these formulas. Right? For instance, if I were you, I would just write out all these charges somewhere. You could do it right here, right? Like sodium is plus and carbonate is 2 minus, for instance. Okay? So go through, write all those charges, use those charges. If you ever ignore charges, you are going to immediately be very sorry. Don't worry at all about balancing until you have all 4 of those compounds written out as formulas. Okay? Get all of those formulas correct. Maybe leave space for a coefficient. Okay? It's often helpful to leave a little space in front. What you should probably get in the habit of, especially if your handwriting is kind of messy, what you should really make sure you do, I would literally draw the little underline to give yourself room for the coefficient. I see lots of people with messy handwriting that try to squeeze the coefficient in there when it doesn't really have room, and then they start making mistakes. So write it out with plenty of room there. On other ones, when we're including phase labels, leave room behind for the phase labels. There are no phase labels on this one. But what's the formula for aluminum carbonate? Al2 CO3 parentheses 3, right? That's because aluminum is 3 plus, right? 3 plus, carbonate 2 minus, plus, minus, minus, okay? Again, if you're not respecting those charges, you're going to have trouble. NaCl I would, if I were you, I think it would be helpful if you could get to the point where you could balance this without writing down any totals. Okay? If you need to total everything up, right, that's great. You know, keep practicing that way. But that just means you need to do a little more practicing. I would, it'll be in your best interest to get to the point where you can take something like this and balance it just by writing the coefficients in. Okay? And then if you want to go back and sum things up to check your work, okay, that's always fine. But for instance, there's a lot of you could go at this really a lot of ways. I see the carbonates. I see 3 carbonates over on the right and just 1 carbonate over on the left, for instance. That was sort of my last little tip there. When you have polyatomic ions, as long as the polyatomic ions stay together, because notice here I got carbonate and here I got carbonate. As long as those stay together on the left and the right, you just count them as groups. Okay? But if it broke apart, if we didn't have carbonate on one side, or even if we had carbonate but then also had just carbon or something like that, sometimes that happens where it partially decomposes. Okay? If that happens, you have to go totally by elements. Okay? And in that case, it's probably best to write it out. But that's not very common. Usually, most of the time, our reactions look a lot like this, where you have all the same ions, just in the new combinations over on the right. Okay? So what coefficient should I put here in front of sodium carbonate, then?
3.
If I put 3 in front of sodium carbonate, that gets my carbonates all set. Okay. What about over here in front of aluminum chloride?
2.
Yeah, you can just look at the aluminum. That. And now I've got 2 aluminums, 3 carbonates, so aluminum carbonate is good, and then sodium chloride, if you did it right, that should equal out like that. My last bit of advice is if you run into an equation that absolutely will not balance, okay, if you've tried balancing it a couple of times and you've erased it and tried again, at that point it's time to go back and look at your formulas again. Okay? I would pretty much guarantee that if you have to try more than 2 or 3 times to get something balanced, one of your formulas is wrong. Okay? Go back, write out the charges again. Okay? Make sure that all of those formulas have been written from their charges, as they should be. Okay? That's the very first thing. If any one of those is wrong, it will pretty much not balance. Okay? So make sure that you're well aware of that. Okay? All right. So